Okay. All right. All right. So today we're going to, now that the recording is on, today we're going to talk about hypothesis tests, and we'll start with section 4.1. And then on Wednesday, we'll continue with hypothesis tests. All right. So let me get the textbook available to you. All right. Give me a thumbs up. Maybe Jessica, Danielle. Yeah, you see it? Okay, good. All right. So why do we want to learn about hypothesis tests? Well, this is really a hypothesis tests are created so that we can answer a researcher's question. A researcher's interested in something, and the question should be something that could be quantified, all right? Something that we can measure and or count. And the whole idea is to see if the researcher's hypothesis is true. Now we have to have another hypothesis, one that is the hypothesis that is basically the status quo, basically what everybody believes now. And the researchers come up with something new, something that's an alternative to the current hypothesis. When we talk about hypothesis tests, typically we will have two hypotheses that will be competing one against the other. So this section here is just introducing to you what's involved with a hypothesis test. It's just very general ideas and how to write them down. And then in the next section, which is section 4.2, which is what I'll cover today, we'll start to talk about how do we judge whether the researcher's hypothesis is whether the sample data that we have supports the researcher's hypothesis. Okay. Message you. Okay. Then I guess you already signed with that one. All right. So, what are research hypotheses? Well, they give some examples at the beginning of this chapter here, like does radiation from cell phones affect brain activity? Are mosquitoes more attractive to someone who's been drinking beer? Oh, that's good. If you want to remember something, should you take a nap or have some caffeine? All right, these are kind of like silly examples. There's obviously much better examples than this. For example, you might want to know whether a new reading program in a school is better than the old reading program in a school. All right, and we might want to measure something to determine that. We might want to know whether maybe there's a political poll, and we want to know if a particular candidate's more popular than another candidate, things like that. So many times we'll have data that will support either support or not support the research hypothesis. Here's an example here. So let's just read through it. Just give you an idea of what we're trying to do. So it says here, does light at night affect weight gain? All right, so numerous studies have shown that exposure to light at night is harmful to human health. A recent study examines the effect of light at night on body mass gain in mice. 18 mice were randomly assigned to one of two groups. There's the dark group, had a normal light or dark cycle with darkness at night, and the light group had a dim light on at night. All right, so you get the idea that we want to determine if light is harmful to mice in this case here. What are they looking at? What are they measuring? The gain in body mass, all right? And it says that it was recorded after 3 weeks, and the results are given in the table here. All right, so there's the data set, and there's the, all right. So basically, these are body mass gains, all right? All these numbers here, and there's the group that was randomly assigned to light at night, and there's the group of mice randomly assigned to regular darkness at night. All right. All right. So if this was randomly assigned to one of two groups, this is obviously an experimental study, right? Because the researchers controlling which of these two groups is receiving light and which is receiving the lack of light. Okay. All right. So the question would be something like, do we see a difference in the average body mass gain between the two groups? What do? So for the light group, there's how many numbers here? There's 3, 6, 9, there's 10 numbers for the light group. Those are for 10 different mice that were in that group. You just average those 10 numbers and you get 6.732 as the average body mass gain. You do the same thing for the 3, 6, 8 mice that were in the dark group. I don't know why there were 10 in the light group and 8 in the dark group. Maybe some mice died, I don't know. But anyway, you average those 8 numbers in the dark group, you get 4.114. Now, you may look at the two numbers and say, yeah, there's a difference. But remember, there is sampling variability, right? Sampling variability. So the mice that we have here is just a sample of mice. And if we had a different sample of 18 mice, 10 in the light group and 8 in the dark group, we might get different results. So we have to determine whether the difference here is significantly different than 0, obviously, because if there's no difference between the two groups, the light group and the dark group, the difference between the two means should be close to 0. Obviously, the difference between these two numbers is not 0, it's positive, right? If we say the average for the light group minus the average for the dark group, that's, what is it, 6.732 minus 4.114, that's 2.618, right? That's a difference between the two. Now here they're just basically creating dot plots for these groups, and then and basically they want to know, is that difference between the two groups, is that significant enough to say, according to the researchers, that light has a bad effect on mice, right? Because of, if you gain weight as a result of sleeping at night, that's not a good thing. So that's what they're trying to determine. The researchers thinking that there is a difference. And then so basically what you have to do is learn little bit of statistics to determine if that difference between the light group and dark group in the sample here is significant enough to make the claim that light does have a bad effect on mice. All right. So that's really sort of an idea of what we're trying to do with this type of test. Now, don't be fooled thinking, oh, I don't know how to do this sort of thing. I'm not a researcher. I'm just a student at Rowan University, and why do I need to know stuff like this? Well, you may sometime in the future, you may be asked to determine whether there is some difference between two groups in whatever you're doing in your work. You could be a teacher, you could be a doctor, you could be an engineer, whatever you're doing, you might be asked to do something like this. And so the actual method that we will go through is not that hard, but it's new. All right, that's what this is all. So if you're not familiar with doing research and coming up with hypotheses, join the crowd. Most people don't when they first learn this. So just keep at it, read everything, follow the logic in the textbook, do the homework, and you'll get used to the language. All right, don't worry about it. This is not meant to be overwhelming or very difficult. All right, but it's new. All right, anyway, what we're going to do, as you'll understand as we proceed, is that we're going to do what's called a statistical test to determine if the sample information, like the one we just went through, is convincing enough to allow us to conclude something about the population. In other words, we conclude about the population if we think there's enough information here that light does have a bad effect on light at night has a bad effect on mice. All right, something like that. All right, now here's where the language comes in, the new language. You have to come up with two hypotheses when we do a hypothesis test. This is true whether you're a beginning student like you guys are, or whether you are a experienced PhD researcher. This is what you have to do. You come up with two hypotheses, and they happen to be called the null and alternative hypothesis. All right, what does null mean? Null means zero, nothing, right? But in the case here, the null hypothesis basically is that in the previous case, for example, that there's no difference between the two groups, the light group and the dark group. The null hypothesis would be saying no difference between the two, all right? Because that's contrary to what the researcher is trying to prove. And then the researcher is saying something like, the average weight body mass gain should be greater for the light group than the dark group. Well, that's called the alternative hypothesis, all right? So the null hypothesis is basically that there's no difference between the two groups. The alternative hypothesis is that that the light group is, the body mass gain for the light group is going to be bigger than for the dark group, all right? So the two hypotheses are there. And the whole idea with hypothesis tests, and this is what you have to sort of get into your mind, and I'm going to give you an analogy to this in a minute, is that you're going to assume up front, before you do any research, before the researcher does anything or collects any data, that the null hypothesis is true. So this is interesting, right? Here's a researcher claiming something. Well, they have to prove it, all right? They're a researcher. This is different. This is new knowledge that they think they're coming out with. So they have to prove it. So the null hypothesis, that there's no difference between the two groups in this case, is the hypothesis that we assume to be true first. And then what we want to see is there enough of a difference in the sample data to reject the null hypothesis that there's no difference and state that the light group has a bigger body mass gain than the dark group, all right? So that process that we go through to determine whether there's enough evidence to reject the null hypothesis is basically what a statistical test does. It allows us to do that, okay? All right, so any questions so far about that? You can unmute and speak up if there's anything that's confusing. We haven't really introduced any symbols yet or anything or any way of writing these hypotheses down. I just wanted to know if what I'm saying so far is clear. Any questions? All right. Now, the analogy I'm going to give you, all right, hopefully will be helpful. I don't know if any of you have ever sat on a jury. Now, if you're of voting age, if you're old enough to vote, you're old enough to sit on a jury, all right? Jury duty. And maybe you haven't received any notice yet, but when you get a notice in the mail that you're being considered for jury duty, you have to respond. It's part of civic obligation. It's not something you could just throw away. So if you ever get this, don't throw it away like it's junk mail. You're actually required by law to respond, all right? And unless you have some really good reason, you have to show up on a certain date, and maybe you'll be part of a jury. Well, I don't know how many of you have watched any TV shows, any types of movies where there are trials, different types of trials. And there's really two types of trials. There's a criminal trial, which is the most prevalent one you'll see on television. And then there is the civil trial, all right? Civil trial would be something like if you were suing somebody because they failed to pay you money or something. So what is a criminal trial? Criminal trial means you've committed a crime. And according to the law, you have to be tried for the crime. Now, if you've watched any of these shows, any of the crime shows, where like Law and Order or something like that, When they try you, they always give the instruction to the jury that the individual is considered to be innocent unless proven guilty, right? And the people who are in the jury, they weigh the evidence that's presented by the prosecutor, and the judge tells them, if you feel like the information given by the prosecutor goes beyond a reasonable doubt, takes you beyond a reasonable doubt, then you should conclude that the person's guilty. In other words, the evidence is enough to reject the initial hypothesis that the person is not guilty. So you always start with not guilty, and it's the prosecutor's job to convince the jury that there's enough evidence to reject that hypothesis that they're not guilty and to conclude that the person's guilty. All right, so the hypothesis test is similar to that. So we can consider the idea that the person is not guilty to be the null hypothesis. All right, we're assuming that up front. Person's not guilty. And then the evidence that we have to weigh is like the statistical evidence, like the sample evidence that we're looking at. And then if there's enough evidence to conclude that the person's guilty, we're going to reject the null hypothesis. We're going to reject in the case of the jury, the jury's going to reject the idea that the person is not guilty, the null hypothesis, and they'll conclude that there's enough evidence to conclude that the person did the crime, that they're guilty. All right. So the researcher is like, the researcher has to do something like what the prosecutor has to do. They have to look at the evidence and conclude whether there is enough evidence in the sample data to reject the null hypothesis and conclude that the researcher's hypothesis is true. So the onus is on the researcher. The researcher has to make this determination. All right. So anyway, let me see if we can have. Here we go. Now, in the symbols that we use in hypothesis test, the null hypothesis is going to be the symbol for it's going to be a big H with a little 0, a subscript of 0 right next to it. All right. So it's H. You usually say H sub 0 is the null hypothesis. So that's what we write. And typically we write H sub 0 and then we put a colon. And in the case here, in the case that we were just looking at, we would say that the mean of the light group is equal to the mean of the dark group. In other words, that's the null hypothesis. That's not what the researcher is claiming, but that's what we're assuming at first. Okay. And then the researcher has to look at the alternative hypothesis, which the symbol for it is H with a little a, a subscript of a next to it, standing for alternative. So the alternative hypothesis would be HA colon, and here we see that the mean of the light group bigger than the mean of the dark, because that's what they're claiming, the researchers claiming. So these are the two competing hypotheses. Typically, we just write the H sub 0. We don't write the words null hypothesis. We just write H sub 0 colon. And notice here, we use the Greek letter mu to represent the mean. In hypothesis tests, when we write the null and alternative hypothesis down, we write H sub 0 colon mu L, L is the subscript, is equal to mu D. All right, the two groups here. And mu is the population mean. So the hypothesis is all about the population parameter. It's never about the sample. The sample is just there to confirm whether we can reject the null hypothesis or not. All right, that's why the sample's there. It's just evidence. But the hypothesis itself is always about the population. Therefore, we use the population mean in this case to represent each group. Okay, mu is the population mean. All right. So this is just an example of how to set up a null and alternative hypothesis. All right. Okay. Again, I would recommend that you read through this. Okay. I'm not going to read every word here, but you need to read through it and look through some of the examples and see if you understand exactly what's going on. So let's do another example here, just to give you an idea of how to set up the null and alternative hypothesis. So here it says a server at a restaurant recently told one of the authors that when diners at a restaurant request a to-go box, what does that mean? At the end of the dinner or lunch, you want to have a little box with the leftovers in it, right? So that's to-go box. Take leftover food home. According to the server, about 30% of the people who get these little boxes to take home at this restaurant forget the box and leave it at the table. All right. I'm sure this has happened to you too. You know, you ask the server to give you a little bag or something, you put it in and then you forget it, right? And you never go back and get it. But according to the server, out of all the people who come to the diner, they believe about 30% of them forget the box and leave it on the table. Now, this is a hypothesis because they haven't really collected any data on this. All right. This is what the server believes is true. All right, so suppose the restaurant plans to take a random sample of 120 diners that request one of these to-go boxes, and they actually count how many of them actually forget to take their leftover food. All right, so they're actually doing some research here, and they want to confirm this 30% or not. All right, so it says state the null and alternative hypotheses in a test, determine whether the sample provides enough evidence to refute the server's estimate of 30%. Now, in this particular case, because the server came up with a particular number, they didn't say greater than or less than, they came up with a particular number. That particular number is the null hypothesis, all right? We're going to say that's a null hypothesis. Now, it's always true that when we have the null hypothesis, we use an equal sign in the null hypothesis. We always use an equal sign. And the alternative hypothesis has three possible symbols. It either can say less than, it could say greater than, or it could say not equal to. All right. So in the previous example, the one that we did with the light and dark, notice that we had greater than symbol in the alternative hypothesis. And in this one, notice what we have is not equal to. Now, you know, any examples I give you, by the way, in a test or in a final exam, it'll be clearer than this example here, what symbol we should use in the alternative hypothesis. But in this case here, we're saying not equal to because we're trying to refute the server's estimate of 30%. So refuting it or saying it's wrong could be the sample results could be less than that, significantly less than 30%. It could be significantly greater than 30%. We're only interested to see if the 30% is right or not. We don't care if it's less than or greater than. So that's why the alternative hypothesis says not equal to. All right. We're not equal to meaning that if we can prove it's not equal to 30%, whether it's on the low side or on the high side, we've done our job and we've proven that the server there was wrong. Okay. But anyway, this is another example. And notice they use P in this case here for the population parameter. Right, now, what is the population in this case here? It would be all diners that have since the diner opened up, all diners who requested one of these boxes, all right? The population of all diners. And it could be maybe hundreds or thousands of these diners, depending on how busy this diner is. And the sample in this case, there's only 120 of them that are being asked or being looked at. Random sample 120 of these potentially thousands of diners that go through this restaurant over the years. So we're interested in making a conclusion about the population. And so we use P. That's the population proportion. Okay, 0.3. Notice they say 30%, but we convert it to 0.3. Okay, so that is how we set this up here. Now, p hat, which is the sample statistic, that's not in this hypothesis test, all right? P hat could be a number that's less than 0.3, could be a number that's greater than 0.3. That's just the evidence. We're interested in setting up the hypothesis first. And that is always going to be the very first step in a hypothesis testing. You read a question and then you set up the hypothesis test. Now, you're not going to be really good at this at first, all right? You may right now be thinking, I don't know how to do that. But that's what the homework is all about, all right? I would highly recommend you read the chapters here, all right? Because it's going to help you. And go into Wiley Plus and do the homework. Now, I've set up homework for sections 4.1, 4.2, and 4.3, and also 5.1, all right? Okay, so we're going to cover 4.1 and 4.2 today, and then 4.3 and 4.4 on Wednesday. There's not going to be homework for 4.4, and then 5.2 next Monday. Be covering that. All right, so next, including today, 5 sessions on hypothesis tests. All right, and then they have another example here where we're looking at, this is an example where the symbol is going to be less than in the alternative hypothesis. So let's just read through it quickly. It says cocaine addiction is very hard to break, even among addicts trying to break the addiction. Relapse is common. Researchers tried different treatment drugs to see if the relapse rate can be reduced. So they did a double-blind experiment, compares the proportion that relapse between those taking the drug being tested and those in a control group taking a placebo. All right, so you have your drug group and you have your placebo group. And basically you want to see if the drug does reduce the relapse, right? Going back to cocaine, that's why you want to take the drug, right? Because you want the addict not to go back to the habit of taking cocaine in this case here. So that means that the drug group, according to the researchers, would reduce the proportion who go back to cocaine relapse. All right, so this is the alternative hypothesis is that the proportion of the drug group should be less than the proportion in the control group that's not taking the drug. The null hypothesis, no difference between the two groups. That basically saying the drug doesn't really help. So the null hypothesis in this case is the drug has no effect. And the alternative hypothesis says it does have an effect. It reduces the proportion of people who relapse. So here's a case where the alternative hypothesis has a less than symbol as opposed to the other two symbols we saw. We saw greater than symbol, we saw not equal to symbol. Okay, we'll talk more about these. I'm just showing you examples of these types of tests. Now, the 3 types of tests that you can have for an alternative hypothesis is, like in this case, less than, or we can have greater than, or we can have not equal to. And those are the 3 types. And we'll use different terms for those a little bit later. We actually learn how to do the testing. All right. So here's a little summary here of what we learned in this initial section here. We need to state, step number 1 in hypothesis test, we need to state the null and alternative hypotheses. The null hypothesis symbol is H sub 0. The alternative hypothesis is H sub A. And these are claims about population parameters, not sample statistics. So we always use the symbols, the correct symbols for mean and proportion. So we're going to use the Greek symbol mu for population mean and the symbol P for the population proportion. Right? It says, in general, the null hypothesis is a statement of equality. So the equal sign will always be in the null hypothesis. And the alternative hypothesis will either have a greater than symbol, a not equal to symbol, or a less than symbol, depending on the question that you're looking at. All right. Now, let's take a look at evidence. All right. And we're just in this preliminary stuff that we're doing here is not very mathematical, but it's just to give you an idea of what we mean by evidence against the null hypothesis and in support of the alternative hypothesis. What do we mean by it? All right, so suppose The null and alternative hypothesis is this. This is what we saw before, where the population proportion and the null hypothesis says the population proportion is 0.3, and the alternative says not equal to 0.3. So suppose we have different samples. We have 4 different samples here of 120 people, all right? And we want to find the number of those out of the 120 who left their to-go box on the table. So one person does a sample of 120, and they found 36 of them forgot to take their box. Another person, 37 of them forgot to take their box. Here's sample number 3, 90 of them forgot to take the box, and the last one, 27 of them forgot to take the box. So the question is, what they're asking here is, which of these samples provides the strongest evidence, all right, against the null hypothesis? What is the null hypothesis? Is that 30%. That's the proposed hypothesis. That 30% or 0.3 of the people who leave these boxes forget about them. All right, so which provides the strongest evidence to reject that? In other words, we want to know which of these samples provides that strongest evidence. Now, can somebody, you can just unmute yourself, take a look at A, B, C, and D. And if we were going to reject the null hypothesis and say it's not 30%, it's something different, which of these provides the strongest evidence that it's not 30%?
C.
I'm sorry, say it again.
C.
C. Very good. Because C, 90 out of 120, I believe, is 75%, isn't it? So that would provide the strong, that's the biggest number or the biggest, that's the number that's the biggest out of those 4 numbers, right? The 4 samples. The proportion is 90 divided by 120, which is 0.75. That is certainly much, much bigger than 0.3. All right, which provides the least amount of evidence here to reject that the proportion is 30%? Which provides the least amount of evidence?
D.
D? Okay, why did you choose D?
Because it's closest to 1. Oh, actually, it'd be B.
Okay, you're getting closer. How about A? A is exactly 30%. That's right. So that would support the null hypothesis, wouldn't it? Because it's exactly 30%. 36 out of 120 is 0.3. So that provides the least evidence to reject the null hypothesis because it actually equals the null hypothesis. All right. Now, B is correct also because it's very, very close to 30%, but it's a little bit more, right? Slightly more. So that provides the next least amount. And then I would go with 27 as the next one. 90 for certain provides the most evidence because it's so much different than 30%. So that's the whole idea, everyone, that to reject the null hypothesis, all right, and support the alternative hypothesis, you need to find, your data has to support something that is far away from the null hypothesis, far away from it. In this case, far away low, right? Because it could have been 10%, right? We had a number, let's say 12 out of 120. That would have been really low. That would have been far away. Or something big in this case. And C, of course, is 75%. So what we're looking for is something that is, in this case, either really low or really high, because it's the alternative hypothesis says not equal to. So it could be on the low side or high side, be different than the null hypothesis. Now, your question would, of course, have to be, how do I know whether something is big enough or small enough, in this case, or different enough from the null hypothesis? How do I know how far away do I need to go to say, all right, the null hypothesis, I'm going to reject it, and I'm going to go with the alternative hypothesis. You get the idea? How far away is it? Now, 90 out of 120, it seems like that's pretty far away, right? And it seems like it's pretty, you're sort of feeling like, without knowing any statistics, that one probably you could pretty easily reject the null hypothesis. However, how about the 27 out of 120, right? The D. Is that sufficiently far away from the 30% to reject the null? And this is where we have to really learn how to do the actual test. Now, going back to that analogy with the criminal trial, if the prosecutor has done a really good job, right, to present the evidence to reject that the person is not guilty, then the jury has there's a good chance the jury will come back with a guilty verdict. However, even if there's convincing evidence, there could be a juror that says, you know what, I'm not convinced enough. And they hold up the whole deliberation, right? Because you need all the jurors to agree the person's guilty. So there's some debate going on. And it's always a matter of determining in a kind of a vague type of way whether there's sufficient evidence. In a statistical test, it's very precise. It's different in this way. In other words, if you do the test correctly, you should come to the same conclusion no matter who you are, all right? No matter how you feel about the numbers. The statistical test will tell you the answer. Is there enough evidence? Yay or nay, all right? Everybody should come to the same conclusion. And that's what we're going to learn how to do, all right? But now what we're doing is just trying to get an idea of what, in general, what we're trying to accomplish. We want to see if there's sufficient evidence with the numbers. Do the numbers sort of lead us to conclude that the null hypothesis is probably not true? All right. Now, one of the things that I have to make really clear to you is when we reject the null hypothesis, we are not saying that the null hypothesis is absolutely false. Okay. It's possible that even if there's a great deal of evidence to reject the null hypothesis, it is possible that we have made a mistake. Now, we're going to talk more about this in section 4.4 on Wednesday. I'm going to talk about this issue because the two possibilities when you do statistical tests is that you're going to reject the null hypothesis or you're not going to reject the null hypothesis, all right? Those are the two conclusions when you do a test. And it's possible that no matter which of these two that you end up doing, it's possible that a mistake was made, all right? So you want to try to minimize those mistakes, but it's possible. Just like in a criminal trial. If a jury decides that somebody is guilty, it doesn't mean they actually committed the crime, right? You have heard of cases where somebody was found guilty, they sat in a prison for 30 years, and then there was some genetic test that was done later to show the person didn't commit the crime. So even in jury, even if there's strong evidence, it still doesn't mean the person committed the crime. Likewise, if you found there was not enough evidence to conclude that the person committed the crime, in other words, you did not reject the null hypothesis, it doesn't mean the person didn't commit the crime. It's still possible they committed the crime. Okay. It was a famous trial in the 1990s. Some of you might have heard about it if you were a football fan. It was O.J. Simpson trial. Okay, and many people felt, not all, but many people felt that he was guilty, and yet he was found not guilty because the evidence was not sufficient enough, according to the jury. All right. So errors can be made in criminal trials. They can be made in hypothesis tests, but we try to minimize them as best we can. All right. I just wanted to bring that up to you. All right. Now, Now, sometimes there's hypothesis tests that are done on, besides the means and proportions, sometimes they're done on other statistics, such as on a correlation coefficient. All right. So we might get for a particular sample, we may get a positive moderate correlation coefficient of 0.43 in this case here. We're looking at football teams and correlation between malevolence of NFL players. I guess that's do with what they're doing, and penalty yards, whatever. I'm not going to spend much time on this. Not everybody knows football, but sometimes if you're looking at a regression or correlation, sometimes you can do statistical tests on some of those measurements also. All right. So don't be bothered that you would see something like this, where the null hypothesis would be the population correlation. Notice that they used the Greek letter rho here, RHO, to represent the population correlation. It says it's 0, and the alternative hypothesis says that the correlation coefficient is positive. It's positive, greater than 0. All right. As far as the actual hypothesis test that we do, now you might see something like this in the homework, but don't worry about it. We don't, it'll just be some general information about something like this that you have to go through. We're not going to actually do hypothesis tests for correlation coefficients. We're not going to do them for anything other than means and proportions. All right. So we're keeping this as simple as possible. That's all you're going to be tested on. And on the final exam also. So we're going to keep this at a minimum. But they do mention other types of statistics and parameters that we could do testing on if we wanted to. All right, so they mentioned them. And here's another example here where they're testing that the mean, in this case, the null hypothesis is that the mean is equal to 80. Alternative is that mean is greater than 80. Now they give the actual example here. They talk about arsenic-based additives that are added to chicken feed, and they say these are banned in Europe, but they're not banned in the United States. Somebody believes, let's see. There's a chain, let's say many restaurant and supermarket chains are working to reduce the amount of arsenic in chicken. To accomplish this, one chain plans to measure for each supplier the amount of arsenic in a random sample of chickens. The chain will cancel its relationship with the supplier if the sample provides sufficient evidence that the average amount of arsenic is greater than 80 parts per billion. So here's a chain that wants to test, always test if the amount of arsenic is greater than 80 parts per billion, right? And they actually think it's acceptable to have less than 80 parts per billion. But whatever. The null hypothesis remember the null hypothesis always says equal to, so equal to 80, the alternative is that it's greater than 80. And if the sample statistics, the sample of chickens has a average amount of arsenic to be greater than 80, sufficiently greater than 80, it's possible they may cancel the relationship with that supplier. All right, that's the whole idea. Okay, so anyway, this is one way of writing the null and alternative hypothesis here. We use mu, the population mean, and then we set up the null and alternative hypothesis. All right. Okay, so let's see. And here's another example here. You might see something like this in your homework. They give you 3 dot plots here. Here are 3 suppliers of chickens, right? And they want to know which of the samples shows the strongest evidence for the alternative hypothesis. Now, alternative hypothesis would be that mu is greater than 80. So we're going to look at the average, and let's look at supplier 1, supplier 2, and supplier 3. Just look at the dot plots. Can somebody yell out and let me know which of these three provides the most evidence against the null hypothesis that the mean amount of arsenic is 80? In other words, which of these three suppliers would you probably just say, I'm not dealing with you anymore? You have too much arsenic in your chickens.
Supplier
Which one?
3.
That's right, supplier 3, right? Because the lowest amount of, out of all the chickens that they supplied in the sample, right? The lowest amount is 80. The average is well over 80. Which of these three suppliers would probably provide no evidence of the alternative hypothesis? In other words, it would be a supplier that we probably would continue to have a relationship with. Which of these suppliers do you think looks okay in terms of arsenic?
1.
Supplier 1.
Yeah, supplier 1, right? The average is looks like it's well below 80, right? So there's only 3 of these chickens that were looked at from that supplier and that were over 80. Almost all of them are below 80. And then the one in the middle, we're not sure, right? It could be, the average could be bigger than 80, and we're not sure whether it's sufficiently big enough to say goodbye to supplier 2, right? So supplier 3 definitely looks like we're going to say goodbye to them. Supplier 2, probably have to do a statistical test on that one. Supplier 1 looks okay. All right, so you get the idea? This is another example of how to, in a very non-mathematical way, a non-precise way, to sort of get a feel for how we're going to do a hypothesis test, right? And what we're looking for in a hypothesis test. We're looking for extreme examples. All right, so that is 4.1. Let's actually go to 4.2. This 4.2 is going to introduce a way of measuring, whether we should reject the null hypothesis or not, right? It gives us a mathematical way of doing it. So just hold on one second. All right, kind of annoying here. Oh, that's right. Hold on. Oh, shoot. What happened here? Right. All right. Sorry about this. This is annoying. All right. So let's go back to chapter 4. And now we're going to go to 4.2. Okay, now this was the other example we were looking at before with the light and dark group. We have our null and alternative hypotheses up here. And here's the sample data. It's down here. Notice that the sample mean is for the light group 6.732, and the sample mean for the dark group is 4.114. And we're interested in the really the difference between the two, right? We want to see if there is a significant difference between the light and dark group, the light, and in particular, we want to see if the light group is bigger, is a bigger increase in body mass than the dark group. That's what the alternative hypothesis here. So we're going to actually subtract these two numbers and look at and see if it's significantly bigger than 0. Now, how do we do that? Well, one way of doing this is to use StatKey. Remember StatKey, when we did confidence intervals, we created what was called a bootstrap sampling distribution. Well, we're going to create a different type of distribution with StatKey, and it's called a randomization distribution. And in this case here, we're going to assume that the null hypothesis is actually true for the population. All right. So we're going to make that assumption. So when we create the so-called randomization distribution using computer simulation, we're going to assume that the null hypothesis is true. Now, what's the null hypothesis in this case? That the mean of the light group and the mean of the dark group are equal to each other. Now, I hope you know mathematically that's equivalent to saying that the difference between the two means, the light group and the dark group, would be zero, right? If they're hypothetically, if they're equal to each other, that means if we subtracted them, it would be zero. So the null hypothesis would be that the light group and the dark group, the difference is zero, and therefore we would have we would create these so-called randomization samples. We would ask the computer to come up with hypothetical samples which have the difference in the means to be zero, as we're assuming to be zero. All right, and we come up with different samples of the same size. All right, and here's an example here that's done in StatCube. So the null hypothesis is that there's no difference in the two means. So the null is zero. Notice it's centered at zero. Also notice that there are 3,000 of these randomization samples that were created. Now you don't have to know, by the way. I mean, you can go into StatKey. They have little videos in there that tell you how they come up with these samples. You don't really need to know how they came up with the samples. Just know that they are hypothetical samples. And they have the same sample size as the original sample. In other words, the original sample has 10 in the light group and 8 in the dark group. And so that will be also true for any of these randomization samples. 10 light group, 8 in the dark group for each one of the samples. And there's 3,000 of these samples here. All right. Now notice the mean is 0.009. That's sufficiently close to zero. And here's our standard deviation, the standard error, 1.288. Okay. Now, let's go back again, look at the alternative hypothesis. There's the alternative hypothesis is saying that the light group is greater than, the mean of the light group is greater than the mean of the dark group. All right. So that's going to have an effect on what we actually show on this graph here. By the way, if somebody else did another sample, all right, and they would come up with different numbers. All right, so they, in this case here, notice that the sample of the mean of the dark group is actually higher than the mean of the light group in this particular sample. Right? If we took the difference between the two, it's actually negative. So some samples are going to have positive numbers that are the difference between the mean of the light group and the mean of the dark group. Some of them are going to be bigger than zero. Some are going to be smaller than zero. It's just sampling variability. All right. And that's what they're trying to indicate here. All right. Now, suppose we created a randomization distribution like the one we just saw. Okay, let's go back. We create something like this. And suppose we have a sample. We have two different samples here that are maybe one of those dots in the randomization distribution. One of them has a difference of 0.75 and the other has a difference of 4. Let's go back to the, actually, let's scroll down. I think they're showing here. Here's again, the original randomization distribution, the one that was shown before. So 0 is in the middle. And suppose that the difference between the two sample means is 0.75. So that would be approximately over here somewhere. All right, so 0 is in the middle, 0.75 is somewhere over here. The question that you may ask is, does that look like it's normal variation that could just be something that could happen whenever we think the population is 0. Does this look like a case of 0.75 where it could just be normal variation? That we could get a sample with a difference like that? What do you think? Do you think that's possible? That if I assume that the population has a mean difference of the means of 0, do we get a sample that has a difference of means of 0.75? You can just answer yes or no. Somebody can yell out, is 0.75 something that could happen with just normal variation? In other words, the normal sampling variability.
Yeah.
Yeah, it looks pretty reasonable that you could get 0.75. How about if the difference in your samples was 4? And suppose it was way out here. Do you think that has a good chance of being due to normal sampling variability?
No.
No, no. It's probably unlikely, right? That if the mean difference is 0 for the population, that we would get an actual sample that would have a difference of 4. All right. So in that case, notice it's extreme, right? It's to the right, way to the right of the sampling distribution. So the ones that are extreme, the ones that are very low or very big, in this case, it would be very big because the alternative hypothesis says greater than. So we're looking at the very big ones. We would probably think that if we got a sample that had 4 as a difference in the sample means, we would think that would be evidence against the null hypothesis that there's no difference in the means. Okay. So we could use this information here, the sampling distribution, to come up with sort of like probabilities of whether a particular sample statistic is extreme, okay, therefore would not be consistent with the null hypothesis. All right, so it says here, the further out the observed sample statistic is in the tail of a randomization distribution, the stronger the statistical evidence is against the null hypothesis. So when we said that the difference in the means was 0.75 and it was over here, well, that's not that extreme. But when we say the difference is 4, it's really extreme. So we're saying that there is more evidence against the null hypothesis if the number that we get for the sample is way out here, as opposed to 0.75. Okay. Now, there's a way of measuring this, how extreme the sample data is with reference to the null hypothesis value. And this is what's called the p-value. The p-values are used straight through the PhD level. But I think a lot of researchers sort of, when they get to the PhD level, forget about what a p-value really is. So let's read through the definition of it, and then I'll show you how it's determined using StatCube. It says the p-value is the proportion of samples. Now, this is the samples in your, right now, it's the number of samples in your randomization distribution. It's the proportion of these samples when the null hypothesis is true that would give a statistic as extreme or more extreme than the observed sample. In other words, if, let's go back to this example here. If our difference in the sample means was 0.75, which would be around here somewhere, where my cursor is, then the p-value would be all these dots to the right of that value. Because we're dealing with a alternative hypothesis that says greater than, we're only interested in this right tail here. Okay. So all the dots that are to the right of the 0.75 would be the number of samples that are as extreme or more extreme than 0.75. Let's look at 4. Well, if 4 is all the way down here, there's not many dots that are as extreme or more extreme than that. So a p-value gives the proportion of these samples that are as extreme or more extreme than the sample data that we're looking at. So the p-value would be bigger for the 0.75 because there's many more dots to the right of it, but the p-value is smaller for the more extreme value of 4 here. So that's the key. The lower the p-value, the more evidence there is that we can reject the null hypothesis. All right. So the lower the p-value, the fewer the dots to the right here, more evidence against the null hypothesis. Any questions about that? Because this is a critical concept. Many students don't get it at first, what this really is, but it's okay. I think this book does a really great job in explaining it. And I would, again, highly recommend that you go through the examples here. But the homework in 4.2 will give you practice with p-values, all right? Now, suppose, here's an example here. So, suppose you have a randomization distribution of 3,000, all right, samples, all right? And we have the light group and the dark group. The difference in the two groups is 2.618, all right? So that's a difference in the means. And if we got onto the figure and we found 2.618 and we counted the number of dots to the right of 2.618, we found 53 of them. Now there are 3,000 samples, so 53 samples had values at least as much as 2.618. 53 divided by 3,000 is 0.018. So the p-value is 0.018. We converted that into a percentage and multiplied that by 100, we would get 1.8% chance, we would say, of getting a sample of 2.618 or bigger. All right, there's only a 1.8% chance of that happening if we assume that there's no difference in means. In other words, we assume that the null hypothesis is true. And we may consider that p-value to be sufficiently small to reject the null hypothesis and say, all right, I think the true population difference between I believe the light group does have a sufficiently bigger weight body mass gain than the dark group. All right. So the p-value plays that role. Now, we're going to even get even more specific. And a little bit later, and we're going to compare the p-value to another number. I haven't told you what that number is yet, but I want you to get an idea of what the p-value is first. All right. Here's another one here. Suppose we had a sample difference in means of 2, right? Or a sample difference in 3. Ask here. Let's assume here's your 3,000. Samples, and we're looking again at the difference between the light group and the dark group for the samples. Suppose that the difference in the mean, the sample mean is 2 for one sample, and for another sample is 3. So I want to ask which one has the larger p-value? Which one has the larger p-value? The sample that has a difference of 2 or the sample that has a difference of 3? Remember, we just count the number of dots to the right, in this case, because it's the alternative hypothesis is greater than. Count the number of dots to the right. Okay. And if we say the sample is 2, if there are more dots than if we say the sample is 3. Which one is it? Which has the bigger p-value?
2.
2, right. Because 2 over here, if you look at where 2 is, to the right of 2, we have all these dots, right? We have a bigger p-value. Look at where 3 is. We have fewer dots, smaller p-value, right? Because it's a proportion. Out of the 3,000, we count the number of dots to the right of that and divide by 3,000. And so the proportions would be smaller for the difference of 3 than the difference of 2. All right? So again, this is, I think this book is fabulous, to be honest with you, explaining this, because most books, they just throw the p-value a concept out at the student, and they expect you to understand. So it says to find the p-value from a randomization distribution. We find the observed statistic in the randomization distribution. P-value is the proportion of simulated statistics that are extreme as the observed statistic, right? And sample statistics further out in the tail of the randomization distribution gives smaller p-values. All right, and we're going to do more examples of this next time when we go into section 4.3. And I will actually go into StatKey and do some examples. So we'll get to see more and more of this next time. I'm just introducing what a p-value is, because we haven't really looked at p-values for where the alternative hypothesis is less than, like in this case here, or not equal to, which I think they have an example coming up here. All right. So we'll do examples, all these examples next time, and do 4.3. And then 4.4 is just, there's one concept in 4.4 I want to cover. You should read through it, but there's no homework in 4.4, but I do want to cover something that I feel is important. All right, so that's what we're going to do next time, 4.3, 4.4, and also we'll work with StatKey just to give you an idea so that when you start doing the homework, you'll know exactly what's being asked. All right, okay, so that is it for today. Now, as far as attendance is concerned, let me actually stop sharing here. What I want you to do, I do have a record of who's here and who's not here, but I do want to, actually, you know what? I'll just go with the record because the Zoom does provide a record of who's in class, who's actually signed on. So I really don't have to ask you whether you're here or not. So anyway, so that'll be it for today. So we'll do the same thing on Wednesday. Just for safety, we're doing this week. We're going to be meeting on Zoom. Next week, next Monday, I'm going to be away, but we will also have a class over Zoom at the regularly scheduled time. That'll be next Monday. And then after that, we'll have 4 consecutive sessions where I pre-recorded the meeting. So as I recommended last time, when it's the class time, just go find the video and watch it as opposed to doing something else with your time. All right, because that time's already devoted for this class. So I will have all 4 videos ready to go by next week. Any questions? Anybody have any questions, comments? Okay, so that's it for today. Again, I don't need to take attendance because I'll be able to tell who's here. All right, good. So see you next time.
Have a good day.
You too.
Thank
Take
you. Have
care.
a good day.
You too. Take care.
Thank you.
You're welcome. See you later.